Stanford University.
And I'd like to express my appreciation for being fourth in this series, because I had the chance to look at the slides from Annie Hazelhurst and also from Mike McGehee, and know that they have really provided a lot of the foundation in photovoltaics that I can build on. So my title is here as an NREL person, but my experience is that over the past several years I've organized an event at the IEEE Photovoltaic Specialist Conference called the PV Velocity Forum, asking the question, what can we do with investors, with regulators, with legislators, with the technology to bring the cost down faster and to bring the scale of the technology up faster? How can we actually, not PV velocity, but how can we accelerate? So as a result of that, I've collected a number of slides from some of our participants, and will be relaying a lot of those findings along with some of my own and some other material from NREL. So just as a reminder of where photovoltaics are, oh wait, I had a title of solar. That was a lie. I'm going to focus just on the photovoltaic part of it. And as you know, the photovoltaics are divided into flat panel technologies that can sit either with a slight tilt on the roof or at latitude. And then there's also the concentrating photovoltaic technology, where you use a lens or a mirror to put intense solar energy onto a higher cost but typically higher performance solar cell. I won't get into a lot of those details. Mike Mike did an excellent job on that last week. But I am going to look at the question of what happens as we begin to grow this industry fast enough to become significant. So let's first of all take a look at the national goal of what we hope to do. Today, photovoltaic systems can provide electricity in the range of 20 to 30 cents a kilowatt hour in many locations around the United States. I guess I should practice using the pointer. So, so that is a number that's about a factor of 2 above where we want to be for the residential electricity prices. Commercial systems are slightly lower than that. And on the utility scale side of the meter, the numbers need to be substantially below that. So we're a factor of 2 to 4 away from where the technology needs to be to run without any kinds of subsidies. In the fall of 2008, the Congress passed an 8-year investment tax credit that provides a 30% subsidy for the installation of photovoltaic technologies. Well, interestingly enough, that's going to expire here in about 2015, which is where our targets are. So the idea is that about the time that tax credit's expiring, we expect that PV will be at a stage where it can run on its own. Many people in the industry think that for some markets in the US, they'll be able to beat that target substantially. And certainly with the recent price drop on PV systems throughout the country as a result of the current economy, that potential is looking quite promising. But even with this sort of a model, you see that the projected penetration here is only looking at a number of about 16 gigawatts overall. So we look a step further, what's driving that plan? And it's the thing called the learning curve, or the experience curve for photovoltaics. What we on the outside can see is the price change, the prices that are being charged for photovoltaic modules as a function of time and capacity here. Inside an individual company, they work with what's called the learning curve, where they're actually working with engineering costs to be able to define how to change their production processes to bring these costs down. So this isn't a picture of economy of scale. This is a reflection of the ability of the industry to adopt new technology that brings a lower and lower costs into production. Now the thing that's interesting is as you go out into these early years, the total level of investment back here was well, at this stage, in the late part of the Carter administration, our budgets were about $100 million a year, and the private sector investment was very, very small, much less than $100 million a year. Through this section, most of the funding was, well, the total funding held flat from here from about 78 through 90, very small in the mid-80s. By the time you get out here, you're now looking at a private sector investment of almost $10 billion in photovoltaics in 2008. So the prices have been coming down. The piece that makes an 80% learning curve is nothing exceptional. It's pretty standard for manufacture of a lot of different products. Washing machines, aircraft, and a number of others fall into that category. Moore's law is an interesting one for semiconductors. It has a learning curve of about 64%. But there are two factors that occur there. There's one is the processing of the wafer, which is coming down on an 80% learning curve. But then there's also the density of the circuitry, which is also coming on a learning curve, which makes the Moore's law so spectacular. So at any rate, the other piece is that with an industry that's growing at 40% a year, many are projecting that you can keep this learning curve going, and by 2020, you would be out with the mainstream of the PV industry delivering product well below $1 a watt, which in a complete PV system would bring the electricity prices down to 5 to 8 cents a kilowatt hour. So the third piece is that one of growth. And the growth in the PV industry has been quite spectacular. Not unique. There are a couple of other industries that have grown this fast. But over the past decade at least, we've established a compound annual growth rate of over 40%. This is a spectacular curve. It makes everybody excited about photovoltaics, and it has very little information. It says that it's growing fast. If you were to do this on a more reasonable curve, you'd plot it as a log. It would be kind of boring. But it would give you the added information that the growth rate here in the last several years has been far greater than 40%. In fact, in 2008, the growth rate was nearly 80%. So that's a little status of where PV is now. Annie Hazelhurst provided a good summary of the economics of PV. I've captured a few of the factors there for your reminder. The key thing is that unlike 10 years ago, photovoltaics is now a profitable business. In 2007, some companies that in the supply chain, particularly the ones delivering silicon feedstock, had profit margins of over 150%. And still, the photovoltaic industry was growing at better than 50% that year. So it's a profitable business, at least for the industry leaders. Even though the current economy has caused the prices to drop from numbers of about $4 a watt in 2007 to numbers that are very close to production cost today. Margins are very slim, but still profitable, with some being sold for less than $2 a watt. Another factor of this industry is in 2008, it sold over 6 gigawatts of electric generating capacity. At a typical price of about $5 a watt for those systems, that amounts to an industry of $30 billion in revenue. As I indicated, in some markets, particularly in peak generation, at peak rates, PV can deliver power without subsidy and at competitive rates today. The Congress passed this investment tax credit, but unfortunately, investment tax credits only work if your investors have profits to write those tax credits off against. So the market has been suppressed a bit in 2008. Some think that it may actually deliver only about 30% growth. And the compound annual growth rate is quite high. But the final piece, I think, is the one where we need to look at why we need to accelerate our growth. At present, an industry of $30 billion still only delivers 5%, less than 0.05% of the US electricity. So what we're going to look at now is how do we change that? How do we get to numbers like 5, 10, 20% of our electricity can be delivered by photovoltaics? By the time you get much beyond that, you're spinning reserves in the utilities, and other factors are going to certainly constrain growth. But within the next 2 decades, there's ample opportunity to insert that much photovoltaic generation into the generation mix. So we take a look in the U.S. Some of the things that will constrain this growth we'll talk about in this presentation include the consumption of materials. Some of you may be aware that in the previous years we had a shortage of the silicon feedstock that's used to make modules. That was largely due to communication between the consuming photovoltaic module manufacturers and the vendors. A new group of vendors entered the industry in order to fill that gap. We'll look at the energy consumption for a module. Typically today, a photovoltaic module has an energy payback period of about 2 years, which means that with a 30-year lifetime, it provides 15 times as much energy over the life of the module as it took to produce that module. There's some of the challenges of raising the capital cost, life cycle issue, and then the biggest challenge of all is how do you tie this significant amounts of power into the grid? So I gave a summary to one of my hosts here and said, as you look at it, if we don't make some improvements here, I've spent my career working in a photovoltaic technology that will be net cash flow negative, consume more energy than it produces, contribute a lot of toxic materials to the environment, and produce electricity that the utilities can't use. It's a great career so far. But there are solutions out there, and we can achieve those. So we'll take a look at what guides some of the projected growth in photovoltaics and the industry as a whole. This is data from the Energy Information Administration that will use their information next to project where we need to be. It's the old adage of it's important to know where you're headed, because if you don't, you may not know it when you get there, from Yogi Berra. But here is an analysis that they've seen of the photovoltaics, and from this 2009 report, they're saying that from an installed base of 30 megawatts in 2006, they're projecting growth to 381 megawatts by 2030. Of course, more than 400 megawatts are installed today. So these are some of the challenges of registering data and projections at the national level in a way that we're all working from the same songbook. But if you look at the planned growth, the Energy Information Administration is expecting that the electricity growth in consumption of electricity in the United States will be substantially below that of the rest of the world. As you look at the 40% growth in photovoltaics, you see that within about a decade, we should, on a global basis, be approaching about 4% of the total generating capacity. Given that the US, from that earlier figure, is really lagging the rest of the world, and we have a vibrant economic base, I projected that, well, we may be able to grow a little faster than that overall, maybe a 50% growth rate, and steal some from the overall global markets, put more of it here in the US, and hit a number of 7%, which sounds good until you hit one of the first constraints. By 2020, this fixed growth rate is going to begin to bump into its first barrier, and that is that this entire economy, this entire country is only adding 1% of its electric generating capacity as new capacity each year. So in that year between 2019 and 2020, this projected level growth rate at 50% a year would provide more than 250% of the new electric capacity that the country needs, which means that if you're going to put that in, you're going to be retiring existing plants. That's a little bit unlikely. And most people aren't looking at that kind of question of how do we make that kind of growth. But unfortunately, I'm a little late. This was a slide that Ms. Hazelhurst presented at the end of October, where she says essentially the same thing. You need to grow faster than the 40% a year now in order to be able to accommodate the limits to growth as you get on out here. And this model starts with a growth rate around 50% in 2010 and ramps down to the point where in 2030, you're down at a growth rate of around 10%. So the challenge is, can we grow at faster than 50%? Well, if you take the total growth in photovoltaic market and plot instead the growth rate, you see some very promising indications that, yes, we probably can grow a whole lot faster than 40%. So what I've plotted here is the growth rate each year by year, and it's pointing up to the kinds of numbers that could make a significant change in the total installed capacity in a hurry. The other thing is that the PV industry has a problem with regard to interaction with the investment community, with the business community. PV has sort of been widely considered to be sort of a visionary technology that's probably not a very good business. The PV industry historically has underestimated its growth rate. It's underestimated its growth rate by 10 to 25% every year for the past decade. These are some studies that were done by Photon International, Navigant, Goldman Sachs, Piper Jaffray, in terms of where the production of photovoltaics would be in 2008, 2009, 2010. These studies were done as recently as 2007, and the first thing, by the data came in for 2008, even the most optimistic projection was well below what was actually delivered. And although there's also some spread in the way these numbers are measured, both of the two leading tracking organizations confirmed that the total growth in PV was far above projections. So it's quite possible that we can achieve the higher growth rates, but there are going to be some challenges. So we'll look at those. As I indicated, materials supply is an issue. A big portion of that's going to be related to your communication with the vendors and confidence in your business. The energy balance, the environmental acceptance. Money is going to be a big issue, is that the capital expense for making photovoltaic modules is quite large, typically 85 cents to $1.50 a watt of manufacturing capacity is the cost of making a new factory. And then finally, how do we get electricity to the point where the utilities can actually use it? So let's take a look first at the material supply. And the historical one of interest really showed up in that growth rate curve. I'm going to back up a couple of slides here. And if you look at the growth here from 2005, 2006, the reason that that number is far below the trajectory was the silicon feedstock shortage. That was largely resolved in 2008. So we take a look at how that got resolved. And keep moving. You look at the projections, is that most of the PV industry was being supplied by the same vendors that provide the silicon for the integrated circuit industry. And based on the projections that they had here, shown in the blue and the purple, the PV industry was going to be staying relatively small and growing at a nice steady rate that would be easily met by the supply from the primary IC industry. But what actually happened was the PV actuals, particularly in the last several years, far outstripped these projections. Began to do that in about 2004. Well, what was happening in 2004 is the German government and several other European countries launched these feed-in tariff programs to stimulate the photovoltaic market. And the overall industry grew to the point where the demand for photovoltaic silicon outstripped the demand for the ICs. And you had a shortage here in 2006, 2005, but by 2008, new capacity, and including some new processes for purification of the silicon feedstock, came online to meet that particular need. Another major technology, one that Mike McGehee discussed last week, was the question of, can First Solar continue to grow as fast as they have? First Solar has been doubling their capacity every year rather than the every 2 years for the industry as a whole. 2010 isn't going to see a lot of growth, but Mike's calculation that they probably consumed half of all the tellurium that was sold last year is very likely correct. If you looked at the change in prices of tellurium between, where's the pointer? If you look at the change in prices from 2007 to 2008 when the First Solar production went up dramatically, you saw a large jump in that. So does this suggest that the CAD Telluride technology is limited to 5 gigawatts annually in total production? Or as Mike calculated, only 680 gigawatts? Well, that's a very big number. That's a great business for First Solar for a lot of years to come. But that's still only about 1/5 of the kind of number that we think that photovoltaic should be able to provide. Well, there are a few things wrong. A lot of this information is coming from the USGS. And the USGS is actually collecting and reporting data primarily from suppliers. And if you look at their analysis of tellurium supplies, it's all coming as a byproduct of copper production. Well, an interesting thing happened in 2008, is that a company called Sichuan Apollo Solar discovered a completely new geology from which they extract a lot of tungsten. And it provides an alloy of bismuth telluride that's quite abundant. Their plans as a corporation is to add another 50 metric tons a year to annual production of tellurium. The other feature is this volcanic source opens up a completely new geology so that you can look for this material in other areas. And I think as Mike mentioned, the amount of tellurium in a CAD Telluride module is very small, so you can pay a lot for the tellurium in order to make more sources economically extractable. But digging a little further into the USGS database, you take a look at bismuth, the other side of this particular compound. And in 2002, their base reserve number for China increased by an order of magnitude. It's also, you notice, an order of magnitude bigger than the entire tellurium reserve, and yet this is a compound that is a one-to-one mixture of the two elements. So one would suspect that as you read the USGS survey that says that most all of the bismuth is provided as a byproduct of zinc production, except in China, which is now 80% of all of our reserves, where it comes from tungsten, that maybe there's going to be an adjustment in the reserve numbers that we'll see in tellurium as well. So the guidance here is that for many of these technologies, the industry will say, if the price of some of my feedstocks goes up some, it will drive the supply industry to seek more sources, and that's good for me. Another side of this is that if I've got valuable materials in my module, that will also encourage recycling of those modules so that they're not left out in a disposal site. So, but the caveat is that in all of these, you want it to be done as a small percentage of the total cost of manufacturing a module. Remember, we're trying to make photovoltaic modules here for a total price that would be well under $1 a watt. So for these materials of cadmium, tellurium, selenium, gallium, indium, you know, the numbers of 1 or 2 cents a watt for the contribution to the manufacturing costs are certainly in an acceptable range. Yeah, darn it. So now let's take a look at how one of these conventional silicon modules is produced. As you go through the making of this module, you see the breakout in costs. Over half the cost of a silicon module is tied up in materials, about a quarter of it in the silicon feedstock to start with. But there are another couple of factors that really have a greater impact on the growth rate for this technology. The first one is the electric consumption, and we'll talk about that quite a bit later. But the other one is the cost of the equipment. In this case, 15% of the cost of that module is due to the depreciation of equipment over a 7 to 10 year life of the factory. So what we're looking at is capital expenditures of 80 cents to $1.50 a watt for installing a factory. So what this means is if you're building a 100 megawatt factory, it's going to cost you $80 million to $150 million to build that factory. Well, this is a factory that's going to generate profits of maybe only $50 million a year. So you're going to be continuing to sink more cash into your industry in order to sustain a growth rate for the overall production. The other factor that concerns me a little bit is with electricity being only 10% of the total cost of the module, this isn't a real big driving factor for bringing down the overall cost. But what we'll see is that in manufacturing a silicon module, the dominant energy consumption part of making that module is right here from making the silicon feedstock and the ingot. And as we look at the progress of the PV industry over the past 15 years, in the mid-1990s, we were using 15 to 20 kilograms of silicon per kilowatt of module production that was put out there. By the mid-2000s, that number was down to 10. Best in class today is under 6. So that driving force of knocking the cost of the silicon out of the module is also knocking a lot of the energy intensity out of manufacturing that module. But let's take a look at where we would be. This figure of gigajoules per kilowatt peak, this corresponds to a energy payback period of about 3 years. If you use that 3 years and take a look at what this industry would do to the overall generation of electricity in the US, we're plotting here the annual deployment of photovoltaics from something that is currently negligible, you know, a few gigawatts a year out of 1,000 gigawatts total capacity, that ramps up at a steady rate of 40% a year until it begins to cap out at a number that's equal to the increase in the total electric capacity for the country. This red line is showing the net delivery of energy from the overall industry, and it's actually below 0 for the entire period, but it doesn't really get significant until you get out here to the point where photovoltaics is a significant portion of the total generating mix. And with that energy payback period, you actually would be consuming 1% of the total US electric generating capacity, or electric consumption in a single year. So the key is we need technologies that drive that energy payback period down. As I indicated, the newer modules that are produced in silicon today would be closer to this number, which is a nice generous contribution, but still the net production is still substantially below what the gross delivery from the PV modules would be by themselves. Again, a company like First Solar is claiming that their energy payback period is now well under 1 year, about 0.85 years. So there are some advantages in the thin film technologies, as there would be in organics or the quantum dots or any of the others that don't need to melt large volumes of semiconductor material at high temperatures, to reduce that energy payback period and be able to remove one of the barriers to rapid growth.
Which technology did First Solar use?
They use a thin film CAD Telluride deposition technology. So we'll now move on to the question of what's the manufacturing and delivery and disposal of photovoltaic modules do to the environment. And here, the PV industry is again becoming a cleaner and cleaner industry for one simple reason, is that the largest part of the emission footprint is from the carbon that's used in the carbon that's produced by the energy that's consumed in the manufacturing of these photovoltaic modules. Again, we're looking at a module here with a payback period in the silicon module between 2 and 3 years. The First Solar or the CAD Telluride technology could be less than half of that. But the other contributions are relatively minor. The balance of systems would include some of the cost of transporting that module to the point of its final application. In other areas, you look at some of the processes that are used in turning these semiconductors into active devices. One of them is to do an edge isolation. So as you make the photovoltaic device, you put it in a diffusion furnace that diffuses a junction all the way around the device. So you'd end up with something that you can't extract any electricity from. So they do an edge isolation etch. In the conventional way, you would stack all of the wafers together and etch the entire side off in a plasma etch in CF4, which has a very high greenhouse gas potential, about 6,400 times greater than CO2. Well, that's been replaced now by using a laser etch that just trims into the edge of that device, and it also substantially improves the throughput of a manufacturing plant. Another example is a lot of the technology for manufacturing thin film photovoltaic modules, particularly the amorphous silicon thin films. This is a slide from Applied Materials showing the growth in flat panel displays. If you go to the earlier sections of this slide, if you go from 1990 up to around 2005, the growth rate here was about 70% when measured in terms of square meters per year total growth. In 2008, the PV industry finally surpassed the flat panel display industry in the total number of square meters of electronic devices that were produced each year. But as a process of cleaning up that reactor in between deposition runs, they use nitrogen trifluoride, which has even a higher greenhouse gas contribution than the CF4. There's a substantial emission of a substantial leakage of nitrogen trifluoride. So now the PV industry, and as well as the flat panel display industry, are looking at replacements for that gas in order to clean up their manufacturing equipment between depositions without the impact on the environment. And finally, this is sort of a more recent issue, is that throughout all of this, I've presumed that photovoltaics are a popular technology, is that any sort of public relations survey of photovoltaics will find that 80% of the population would like to see more solar energy technology in the energy mix. Well, that's already changing. In some of the installations that were intended for desert areas in California, environmentalists were concerned about what this technology would do to the desert environment. I guess one of the questions is, how fast can a desert tortoise sprint from one edge to the other of a 1 gigawatt photovoltaic array? But it's a substantial challenge, you know. So we need to be looking at how these systems can be installed. without damage to the native environments. And the good news here is that our studies from Navigant and others are showing that in the United States alone, there's easily enough rooftop for about 650 gigawatts of photovoltaic capacity. Again, remember today we're less than 1 gigawatt of total capacity in photovoltaics in the US. That would be enough to provide more than 20% of the total electric generation, even including the fact that PV only runs during the daylight hours. Some of the factors you look at in this estimate, a question that my colleague asked earlier is, well, why is the Northeast so small? Well, a lot of those roofs were eliminated because of snow load. As you look at a roof in the Northeast, you may only have 3 pounds per square foot that you can add to that roof. Well, there's only one technology that does that right now. It's amorphous silicon flexible array. So, this calculation has been done taking into account those types of factors. Which leads me now to the question of how do we make this electricity usable to the utilities? And this is really an interesting challenge, is that it's taken about 30 years to develop acceptable standards for the installation of photovoltaic systems onto the grid, the interconnection there. And the basic standard is that the PV will do no harm. I mean, the assumption is that photovoltaics are less than 0.1% of the total penetration, and and whatever you do, don't cause us any problem. One of the biggest questions for utilities is if you connect a distributed generation source into the grid, and the grid goes down, how can you be sure from the utility that your lineman that goes out to fix the grid isn't going to be injured by a photovoltaic system that still stays connected? That's known as islanding. So the primary characteristic of the current standards are that the photovoltaic system will disconnect with either a variation in frequency or voltage, which would be one way of sensing a utility problem. Recent improvements now have anti-islanding circuits in all of these inverters. Well, as long as you're less than a few percent of the total generating capacity on a particular circuit, that's fine. But if you're up at 10 or 20%, and a change at that of a photovoltaic system kicking off is going to be more than the spinning reserves that the utility has going on. So if you get to high penetration levels, you need to be able to institute dynamic control and communication into your inverter. I mean, think about it. You've got an inverter here that's continuously sensing the voltage, the frequency, and the general operation of the grid at that point where a system that the utility didn't even have to buy is connected to their grid. In many of these systems, they're connected to the internet such that the homeowner can do a wireless check of the performance of every module in their particular array. And what do we do with all of that information? We kick the PV system off if there's any variation in voltage or frequency. So as the country moves on towards a smart grid, you can take advantage of that information that the smart inverters are already collecting and be able to provide a more stable grid. Actually, with the inverter technology, you can even use the photovoltaic systems to help meet some of the reactive loads that can destabilize a grid driven from all of the conventional sources. So here's an extreme case I'll describe, where you've got a small village with 20 homes that are feeding. It's in a midtown location. Relatively antiquated. It's what's called a radial distribution network rather than a secondary network that would be in many cities. This particular village is supported by two 75 kilowatt transformers, and as you look at the performance of this, the red curves here are the solar output. The blue curve is the generation, the red curve is the solar intensity. The blue curve is the total power delivered or consumed by these 20 homes with electric systems, photovoltaic systems on them. And you can see that the maximum output is over 100 kilowatts, whereas the maximum demand is under 80 kilowatts. So you've got a system that is really bigger than the overall utility. It runs the risk of driving electricity backwards into the utility system. The utility protects itself from that. It has isolation circuits such that if this were allowed to happen, these homes would be kicked off. So in this particular village, there was something interesting. In order to avoid being kicked off, they actually installed resistive loads to dump that power. In this case, space heaters that were acquired from Sears. And you'll also notice that on the final day, when the sun was very small, they had no load. Well, this is a particularly peculiar village. This was actually the solar decathlon competition in Washington, D.C. last year, which for the first time incorporated grid-connected PV systems as opposed to standalone and battery-connected. But as a result of that experiment, the engineers at NREL and DOE and all of these universities and PEPCO began to understand a little bit more the challenges of being able to interconnect photovoltaics at a high penetration level into the utility grid. So in conclusion, I'd like to remind you that we're a vibrant industry. It's a rapidly growing business that at this stage is not providing a significant amount of energy. But it can grow fast enough to be able to do that. As PV makes this transition from its business success, it's been a number of stocks have done very, very well over the past few years, although this year is, they haven't been immune from the other problems. As we move towards a larger scale, towards energy significance, even a technology as apparently benign as photovoltaics is going to have some pretty large targets on it for critics. We need to be proactive about how we remove these targets, and the good thing is that many of the steps that we need to reduce the cost of the photovoltaic technology, reduce the capital expenditures for the manufacturer, reduce the energy consumption, all of these go hand in hand with making a lower cost, higher performance technology. So we don't have trade-offs here. We just need to move a little faster. And then finally, the biggest concern is if we really can move this fast, the 20 years that it took to get the existing codes and standards in place, that we'll have to replace those codes and standards with new ones that allow for much more sophisticated communication and interaction between the inverter and the utility on a much faster, certainly much faster than 30 years. We'll need to be doing that in 2 to 5 years. All of this, particularly as you look at the intelligence and the data monitoring that's going on in inverters today, suggests that the photovoltaics and other distributed generation really can facilitate a faster adoption of the smart grid. And I understand you'll have ample opportunity later this spring to learn about electric grid and hopefully the interaction of distributed generation sources. But it's been a great pleasure to be invited out here and have your attention, and I really appreciate your attendance, and we'll be glad to take any questions.
Okay, so I'll help you with the question. Any questions? Let's see. Okay, how about back there?
On slide 22, I didn't quite understand a couple of the numbers.
22. Okay. So what you're looking at is the carbon dioxide equivalent greenhouse gas emissions over a life cycle analysis of the PV systems. This is work that's been done by Vasilis Thanakis at Brookhaven Laboratories. He's organized a number of symposia on the life cycle analysis of photovoltaic systems, one at the MRS in 2006, and then most recently it was at the IEEE Photovoltaic Specialist Conference this summer in Philadelphia. So what he's concerned about is if you take a look at the life cycle from how do you manufacture these to how do you dispose of these, how can we reduce our environmental footprint? So what we're looking at here is essentially the energy payback time of a photovoltaic manufacturing process, but now quantified in terms of the amount of CO2 that would be emitted from the energy sources that are used to produce these. One of the things that's, he's actually done analysis comparing the production of a photovoltaic module in China, where the CO2 emissions per kilowatt are higher than in the US. So he's looked at this geographically as well.
So is the smaller is better?
Smaller is better.
So why is a European system with frame in a lower light production environment at a lower efficiency module got a quicker payback than a ground mount US one with roughly double the sunlight.
I don't know. I don't know the answer to that. I was going to say it would be the steel in the frame, but the balance of systems cost here is about the same. I mean, the steel and the support structure for a ground-mounted one versus the rooftop, but that's not consistent with the fact that there's a balance of system component up there, which would include the frame.
There's a huge difference in sunlight levels as well.
This one was for a southern European location where the difference wasn't as great as it would have been in Germany. So that's not the factor. I think that there may be a difference between the difference is all showing up here in the deposition process for making the CAD Telluride.
Is it due to the assumptions on the energy mix in the US and in Europe?
That would be a part of it. But I think the bigger difference is that this module may be a single glass module with a polymer backing, and this is dual glass module, and most of this energy is actually for the manufacture of the glass.
So they're not the same.
Different manufacturer, yeah. This one would be like from a company I think was called Antec, and this would be First Solar. But that's a guess. I don't know for sure.
Is the assumption that the energy use and manufacture is equivalent to the country average really valid? I mean, we used to produce aluminum in the Columbia River Valley off of basically surplus electricity from hydro. Isn't polysilicon and at least aluminum for the frames also produced in these, from cheaper electricity sources?
Yeah, but this is kilowatt per kilowatt. If it takes, I mean, the photovoltaic module cost analysis I had, 10% of the cost of the module, or about 20 cents, is involved in the electricity. So, that was actually an analysis. Yeah, so the cost of it is in there. The CO2 cost should factor in. That's where I was saying is the NACAS has also looked at this analysis depending on whether it was made in an average location in China, average location in the US, or average location in Europe. Certainly, if you did your PV manufacturing with hydro, that would help this balance quite a bit. Yeah.
What percent of the modules are made in the United States today, and what percent are projected to be made in the United States in the future?
That goes back to one of my very early slides. The total U.S. production was only about 300 megawatts out of the 6 gigawatts last year. So two of the largest manufacturers of U.S. orientation are First Solar and SunPower, but the bulk of First Solar's modules are made in Malaysia, and SunPower does most of their manufacturing in the Philippines. So that's not counted into the U.S. total. Yeah.
Do you consider this stuff commercial?
Yes, it's well, yeah, it's a business. It's in most areas it still needs some subsidy, but there are some segments of the market that are being sold based on projected energy prices and the ability to lock in current rates.
How much money does the NREL and the Department of Energy spend on R&D dealing with solar energy?
The Department of Energy's budget, total budget for solar energy this year is $240 million. The NREL is a portion of the total Department of Energy budgets. Ours are 75 million out of that.
So if you have a commercial technology, why does the government have to invest now in R&D?
Well, there are a number of reasons for that. I think that there are 5 reasons. The capital expenditure is too great for the current manufacturing. The energy consumption's too great. There are environmental issues, and we need to figure out how to use this, generate electricity such that utilities can use it. That was the primary theme of my presentation. Now, the vendors are, but yeah, and that's one of the things that's difficult, is when you look at the $10 billion investment that was placed in by private investment and equity investment, most of that was for capacity expansion. The research budgets are a relatively small portion of total revenues. So when you look at how much of the total sales revenue out of that 30 billion actually flows back into research and development for lowering the cost of photovoltaic, still by a factor of 2. You're looking at a total private investment that's roughly equivalent to what the federal government's providing. So it's part of the challenge is that if you want this as an option to provide significant amount of power, it does require some government investment.
Okay, another question. Yeah, how about there? Yeah, you.
My question is about the cadmium Telluride solar panels and the concerns about cadmium's toxic effects, and whether there's any concern about the degradation, whether it's been studied enough to make sure that it won't degrade, and also I heard that there's a layer of cadmium sulfide in the cadmium Telluride solar panels that in its production it can have some waste cadmium, if you think that's a concern with like those scaling up.
As I understand it, you should have asked Mike McGehee that last week. Let me take that question. A big portion of the environmental footprint for photovoltaic modules is how do you dispose of them? And one of the things about disposal is it's grossly unfair, is that from the operator of a disposal facility, they look at the percentage of toxic materials as a function of the total weight. So the tests that are done, and First Solar has done these tests, is you take a photovoltaic module, crush it up, and leach it, and determine what portion comes out. So if you're making a cad Telluride module with 2 sheets of glass, and the cad Telluride is only 2 microns thick, the percentage of cadmium in that total volume of material is small enough that it does not qualify as a toxic waste. As opposed to a silicon module, where you have 1 sheet of glass, a silicon solar cell, and soldered interconnects. In some modules, those soldered interconnects still include lead in the solder. So that silicon module might very well turn out as a toxic waste. So those are some of the, those are some of the same difficulties in, well, we didn't quite think of that, that we have with how do we interconnect high penetration of PV to the utilities, how do we do some of these other things. So there's no perfect solution. The cad sulfide and cad Telluride don't really present any difference in terms of manufacturing hazard or other things. Another feature to pay attention to is cadmium is a toxic material, but cad Telluride is not. It's that cadmium is bound up firmly in a compound. They've done fire tests where you simulate having the cad Telluride module on your roof during a home fire, and it does not provide a toxic emission. So is it a perfect solution? No. But the energy payback time is half of what a silicon module is. If you compare the amount of CO2 that's emitted from making a silicon module versus the cad Telluride module, is the hazard of cadmium enough to outweigh that? It depends on the market. In some markets, Japan in particular, they don't allow any product with any cadmium in it. Nickel-cadmium batteries have been outlawed there for many years. But as you grow this industry, the kinds of questions you ask are going to require trade-offs among the various technologies and smart solutions, such as some of the ones you heard last week.
Okay, more questions. Okay, how about over there?
Would you comment on the effectiveness of government subsidies or government incentives in this country compared to a much smaller European country that doesn't have much sunlight, that has a lot more solar activity than we have?
Yeah,
what are the differences in the governmental actions that cause this?
Up until this year, Well, there's a couple things. If you go back to 1995, the Japanese came up with a very innovative subsidy that looked at that learning curve and said, look, if we start with a 50% subsidy, we can probably ramp that down such that by 2005, we'll only need a 10% subsidy in our country for PV to be used and PV would provide electricity at retail rates throughout that entire 10-year period. And that's exactly the plan they did for 10 years. The German subsidy is very innovative in that it doesn't subsidize the capacity of installation. It actually buys the kilowatt hours, the stuff that you really want. And it's a feed-in tariff. Now, the problem with the German subsidy and the benefit to the PV community is they provided a flat feed-in tariff on the assumption that the cost of the PV systems would go down. And about a year or so ago, they said, look, we're only going to pay the feed-in tariff if this new PV system is cheaper than the one last year. So they adopted some of the thinking of the Japanese program. Now, if you go from 1990 through 2008, all of the action in renewables, in solar, in the United States was done at the state level. It was the California incentive that made California, I mean, the joke is the three leading countries in the world are Germany, Japan, and California. But that's because of the subsidies that happened at the state level. So part of the problem in the US is that the subsidy was not even started until October of 2008. And it's a flat 30% investment tax credit, although now there are grants that are coming out from the Treasury to counteract the fact that about the same time it was passed, all of the profits evaporated. So it's there.
Obviously, the German system worked better.
It was more aggressive. It was very lucrative. You could put in a PV system and make a lot of money. In the US, the subsidy's enough to put in a PV system and have your electricity at your current prices and assume that in the future, utility rates are going to be higher, so you've got a locked-in good deal. So yeah, the German subsidy was certainly more generous.
You just said, so assuming electricity rates are going to rise, I know like California with recent public utilities commission just passed, I don't know what it is, but like tier 1, tier 2 rates, at least residences are locked in for I don't know how long. So is that something that, I mean, I guess that'll raise peak prices. Is that good? What would be better, to have the tier 1, tier 2 rates kind of raising up from the bottom, or to have peak, just concentrate on rising the peak? Do you understand that?
I'm going to plead I'm not an economist on that one. You know, particularly, I don't know the specifics of the California requirements there. So, the Energy Information Administration again is projecting that utility rates will rise nationwide, will rise at about 0.5% per year, greater than the overall inflation rate. And so that that's going to be, I mean, you start thinking about it, energy is such a big component of all of the other costs that if it were much greater than inflation rates, then it would pull inflation rates up with it. So, but you know, that's the other famous line. Predictions are always difficult, particularly if the future is involved.
All right, we'll take one last question. Actually, we'll take two last questions. This one here, and then you in the back, and then
I'm interested in the lifetime of the panels. And consuming 30 years, which is a normal thing people engineer to, some of them are obviously going to go longer. Can you discuss what are the factors that affect the lifetime of the solar panels?
That's one of the, I think that was tied to a question that I failed to answer a little bit earlier. Have some of the newer technologies been adequately tested? For the silicon modules, where much of the encapsulation system is pretty similar to where it was 20 years ago, you have real field data that allows you to have confidence in your warranties. The challenge of developing accelerated life tests is that you don't know whether you're accelerating the correct factors. So until you have like 3 years of field data, it's very difficult to do accelerated life tests where you think you have confidence in 1 year. So I mean, a factor of 3 is a big number. So I mean, the challenge is you can make a very aggressive accelerated life test. For instance, if you wanted to test the life of an egg, you could boil it at 212 degrees. You'll get a different result than if you left it at room temperature for 3 days. So you have those same challenges in testing photovoltaic modules. The typical problem in a module is going to be water vapor permeation, and it's due to the polymer backskin and things, but most of the water vapor comes in from the edges, and that can begin to cause some corrosion. But those are pretty well, looking at one industry study where they were able to accurately analyze and model the peeling rate for the encapsulant off of the top of one of the metal fingers in a photovoltaic device. So they're getting a good handle on that one in some of the technologies. In the other technologies, they're getting the field test data now that allows us to reliably produce accelerated life tests. And some of the modules are showing unexpected degradation mechanisms. I mean, in copper indium diselenide, the top contact is made with a transparent conducting oxide called zinc oxide. It's exceedingly sensitive to water vapor, somewhat similar to some of the problems you have in organic devices. And developing an improved water vapor barrier is a significant challenge, and it's one that's being addressed with government funding.
Okay, back there, last one, and then we'll wrap up.
On the slide 1 or 2 before this, what are the assumptions, if you can flip the slide or 2 back?
For the back?
Yeah, that one.
That one?
What are the, no, that one. Yeah, what are the assumptions in growth rate? Is it the steady?
It's doubling every 2 years, 40% a year.
35% annual growth rate, which is not really realistic as you get further out.
And that was my point earlier, but as you can see, it tapers off here. So it's growing at 40% a year through here. And just the analysis that Annie Hazelhurst did on the 28th, where you say you can't maintain 40% as you get up here as a significant portion of the total generating capacity over here. So I flattened it out to the point where in these final years, you're adding capacity that just equals the total new electric capacity for the US. And when that begins to flatten out, then the PV systems contribute vast amounts of electricity. And because you're no longer building the factories that consume the electricities that last year's modules were producing.
It's also, perhaps I guess it's a little pessimistic to assume that the energy payback time is going to stay as high as 1.7 years. It should be steadily coming down, right?
It has been. And that was the slide that I presented right here, where it's dropped from, this is about 3 years, so that was about 6 years a decade ago. And today, this 3 years is more like 1.7. So it is coming down fast. And thin film technologies, at least the CAD Telluride technologies, is under 1 year.
And that's just for the module?
That is just for the module.
Okay.
Well, no, this one actually includes this one includes the frame. It does not include the balance of systems. So the balance of systems would add another small component on top here. The balance of system being the copper wire to connect them and the structure to hold them up in the wind.
Which will become a growing fraction as the module shrinks.
Steel is not getting a lot less expensive to make. So yeah, it becomes a growing factor. That begins to put in a bottom for where you can get. But then the efficiency of the module changes. I mean, if you start making 20% efficient modules like SunPower is doing today, then you need a smaller structure to create the same amount of energy. So bringing the efficiency up, bringing the energy intensity down, and being smarter about how you interconnect these modules all drives the total energy consumption of the process of putting PV in place to a lower and more acceptable number.
Any sense how much of the energy is in the inverter?
Very small. Smaller than any of these components. The aluminum in the frame is actually more than building and most of the energy in the inverter is in making the steel box for it.
Anyway, thank you.
Thank you.
Much.
For more, please visit us at stanford.edu.